Hi, sorry I couldn't be with you guys today. I'm off on a field trip for honors molecular biology. First thing I want to point out is that you do have homework. Section 11.3, questions 1 through 6. They're due next class, okay? The sub will hand out a colored periodic table for you. You will also see the same picture of the colored periodic table in the notes. Other than that, watch the video and then do your homework. Now, what we're basically trying to do in this set of notes is talk about how electrons are organized inside an atom. Okay? Now, at the end of the last class of notes, not the lab, we talked about what model is the current model of the atom, and that's Schrodinger's quantum mechanical model. All right? Now, in that model, he defines what an atomic orbital is. An atomic orbital is a 3D shape that is set by the square of his wave function that has a 90% probability at any given time that the electron will be located in that specific orbital. Now, the orbitals all have all sorts of different shapes, and we are going to cover that first, and then we're going to talk about how you can assign electrons inside an atom to specific orbitals. Now, there's 4 letters that designate the types of orbitals. They are S, P, D, and F. Each of the 4 different types of orbitals has different shapes. S has 1 shape, which is a sphere. P has 3 shapes, which look like dumbbells. D has 4 shapes. F has 7 shapes. Each quote-unquote shape can hold up to 2 electrons. No more. So, again, atomic orbitals, 3D space, hold a maximum of 2 electrons. S orbitals are spheres. So, they're shaped like a sphere. They're centered on the nucleus. And the way it works is every period of the periodic table has an S orbital associated with it. Really, the periodic table, as you're going to see, is sort of organized into energy levels. And you'll see that on the handout that I have the sub give you guys. So a 1s orbital looks like a sphere centered on the nucleus. A 2s orbital is also centered on the nucleus, and it surrounds the 1s orbital. Now, there's a bunch of other shapes as well. P orbitals are shaped sort of like a dumbbell. So you can see that there's 3 of them, one along the x-axis, one along the y-axis, and one along the z-axis. And they all stack on top of each other, again, centered around the nucleus. We actually refer to them as px, py, and pz. Each individual px, py, or pz is also referred to as a suborbital or a sublevel. Each can hold 2, and if you look at your handout periodic table, you will see, for instance, if you look where it says 2p, starting with boron, all the way over to neon, you will see that there's 6 total elements covered in that region. And really, this is trying to show where the electrons are for those elements. 2 for neon would be in the X, 2 would be in the PY, and 2 would be in the PZ. Now, this is when you have all 3 suborbitals overlapping. D and F orbitals are even weirder shapes. I'll show those in a minute. But in the meantime, I want to play you a video that I made last year when I was out of, actually 2 years ago, when we were first out on COVID, that talks about atomic orbitals. All right, give me a sec. Looks like I have the sound off, so I will put the sound on. Let's see. Could have sworn I had it on, but I guess not. All right, now I'm trying to show you the shapes of the orbitals and give you some sort of a feeling about how they stack. So 1s orbital is a sphere. Let's call this a small little 1s orbital. That corresponds to the first period on that periodic table that I gave you, the colored one. So that 1s orbital is all hydrogen and helium have. Now if you get onto the second period, the first two elements, that's lithium and beryllium, they have a 1s orbital and a 2s. Now, I don't know if you can see, but there is a 1s orbital inside my 2s orbital. I don't know if you can see that or not. Hopefully you can. All right, I blew a balloon inside a balloon just for fun. I couldn't do two balloons inside a balloon to give you a 2s and a 1s inside a 3s. But as we go across the period though, the second period, we start to hit things like boron. Boron has p orbitals. So p orbitals look like dumbbells. So they also, I'm putting on the letters for the orbitals. So there we've got 2px, 2py, 2pz, but they don't exist like this in 3 dimensions. Let's see if I can get these put together without popping them. That's always the key thing. Come on. There we go. You see how they're, whoops, except the wrong sides. These two are on the wrong sides. There, now we got it right. So you've got your 2py, the purple one. You've got 2pz, the orange one. And you've got 2px, the green one. Now inside that, centered, the nucleus would be where the balloons all intersect. You would have jammed in there a 1s and a 2s orbital. Now these aren't really drawn or shown the scale. The 1s and 2s would be bigger. It'd be a slightly smaller than the extent of the 2p, the 2s would be. And then if you go to the next period, you get on to the third period, and you get down to, I don't know, sodium and magnesium, there's going to be a 3s. And that 3s, again, this isn't to scale, but the 3s will be around these two, and then you'll get 3p, which will be even bigger than the 2p. So you end up with these things all stacking on each other with the nucleus at the intersection of all the balloons. That's pretty much the activity that I did in class with the balloons. If you look around the classroom, you can see the balloons, labeled just like in the video. Now, this is what the d orbitals look like. You do not need to know the shapes of the d orbitals. You do need to know the shapes of the s and p orbitals. The key thing about d and f orbitals is how many different shapes there are. Each of these is a suborbital or a sublevel, depends on the textbook how they're described. Because there's 5 shapes, and each individual shape can hold a maximum of 2 electrons, there's a maximum at any given energy level of 10 electrons that could be in d orbitals. F orbitals, similar to d orbitals, have very weird shapes, but there's actually 7 of them. So again, each shape can hold up to 2 electrons. 7 shapes means 14 total electrons. Now, if you look at the colored periodic table that was handed out, the orange block on that refers to the F block, and you can see it's 14 elements wide. If you look at the green block refers to the D block, all right, and it's 10 elements wide. 10 elements wide means 10 total different electron changes. 10 electrons can be in D. 14 wide means there's 14 electrons. You can have 7 shapes for F. This is just a kind of a overall picture that just shows all the shapes next to each other. There are no other shapes beyond F. There's just S, P, D, and F. Again, make sure you know which one's shape is the correct shape for S and the correct shape for P. Don't need to know D and F. This is basically a copy of the colored periodic table that should have been handed out to you. If it wasn't, it's in the notes, and so you can always print it. Where can you find the notes? Before we finish, why don't we take a real quick look. Where can you find my notes? So if you're wondering where these notes are, they're in Modern Atomic Theory and Bonding. Scroll down, we're in the 3rd week, and bonding notes, colored periodic table, and fun with balloons on day 3 is where we're at. The fun with balloons is the video that I showed you already, all right? If you don't have the colored periodic table, if you didn't get it in class, you can print it here, and the notes that we're going over on this video are right here. Now, there's a couple more topics that we have to talk about. First is valence electrons. Now, we referred to valence electrons before, way back in September, as the outermost electrons, and those were also the ones that were in our ring diagrams for the outermost ring. Well, we know that electrons are not on rings. They're in atomic orbitals. All right, so how can we take that old knowledge and apply it to the new model that we have? So valence electrons in all these models are involved in bonding. However, the valence electrons, and they're the farthest ones from the nucleus, so that's still consistent with everything we had before, but the difference is that the valence electrons correspond to the electrons in the s and the p suborbitals of the highest energy level the element is located in. So for instance, let's take a look at germanium. That's Ge. Do you see it down in the 4p level? Okay. If you want to know how many valence electrons germanium has, you go down to the 4th energy level, which corresponds to the 4th period, and you start counting the spaces that are pink or blue left to right. So you can see 4s, there's 2 in that space, and then we get to 4p, gallium, and then germanium, and we stop when we hit germanium. So 1, 2, 3, 4. Oh, there's 4 valence electrons for germanium. D electrons are not valence electrons, nor are F electrons, F block electrons. Now, electron configurations are a way for a chemist to tell other chemists exactly where the electrons are located inside an atom. It's a way of writing their locations based on Schrodinger's work and atomic orbitals. Each element has a unique arrangement of electrons called its electron configuration. And so now we're going to talk about basically how can we assign them. So an electron configuration is a number that signifies the energy level. Look at your colored periodic table. The energy level is on the left. It also corresponds to the period the element is found in. Look at number 2, all right? The letter indicating the orbital is the second thing that you're going to have. So if it's a S, it'll be S. If it's a P, it'll be a P. If it's a D, it'll be a D. We don't use the suborbital designations like X, Y, X, Z, or X or Z. So PX, PY, or PZ. I mean, we don't use the subscripts. We just call it a P if it's a p orbital. And then finally, there's a superscript indicating how many electrons are in the orbital. So S can hold a maximum of 2. Because P has 3 different suborbitals, each holding 2, overall a p orbital can hold 6. D has 5 sublevels, each able to hold 2. Overall, a d orbital can hold 10. F has 7 suborbitals, so each which can hold 2, so it can hold up to 14. Now, the orbitals are going to fill in the order on the colored periodic table from left to right to top to bottom. So let's go through some examples. All right, so here's a bunch of elements. Hydrogen. Where did I come up with 1s? Find hydrogen, the symbol on your colored periodic table. Do you notice that it's in the first energy level? That's the first number. Second, it's in the S block, which is pink. Second letter is S. Hydrogen only has 1 electron in that orbital, so the superscript is 1. Helium is the next one in the level 1 S block, but helium has 2 electrons, so its electron configuration is 1s2. Lithium now is in the second energy level. It has 3 total electrons. Remember, we're going to fill left to right, top to bottom. So in order to put 3 electrons into atomic orbitals in lithium, 2 of them have to be in the 1s2 because that's at the top. Drop down to the second level, and the 1 electron there is in the 2s1. Is 2s, so there's 1 in that space. Beryllium, the next one over, 1s2, 2s2. Now keep going across. When we hit boron, we start a new shape. We start p orbitals. So again, everything fills top to bottom, left to right. So the boron electron configuration is 1s2, 2s2, and now we're over to the p orbital. There's 1 in the p orbital. Now, p orbitals can hold up to 6, d orbitals up to 10, f orbitals up to 14, s can only hold 2, period. So we keep going across: carbon, nitrogen, oxygen, fluorine, neon. Neon is the end of the second energy level or second period. Now, do you notice I wrote neon 2 different ways? One way I wrote it out, what I would call sort of the longhand electron configuration, 1s2, 2s2, 2p6. By the way, the superscripts tell the total number of electrons. Neon, if you look on the periodic table and count, it's got an atomic number of 10. It's got 10 electrons. The superscript should add up to the atomic number. Now, why did I put brackets around neon? Brackets around neon mean this electron configuration, 1s2, 2s2, 2p6. It is part of what is called electron configuration shorthand or noble gas shorthand. Look at sodium. We're down to the third period now. This is written out in longhand. Do you see that there's one electron in the 3s atomic orbitals? That's why 3s1 is the last one. But we can abbreviate that by putting neon in brackets and then saying 3s1. Neon in brackets means 1s2, 2s2, 2p6. Go to magnesium. Same thing. We can write it out the long way, or we can abbreviate it using the noble gas shorthand. Now, that's all there is for notes. Take a look at the homework. Read through the section. All right. So get your notes together and then do your reading and answer the questions. You can probably